A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. The next time you ask an LLM a question, you're not just paying for a few cents of inference. You're paying down a foundational training debt that costs more than the GDP of a small country. Today, we're itemizing the bill for the most expensive autocomplete engine in human history.
Herman Poppleberry here, and that is an excellent way to frame it, Corn. We are talking about the pre-training phase, the absolute stage zero of artificial intelligence. As of April 2026, the price tag for a single frontier model run has reportedly crossed the $500 million mark. That is a staggering barrier to entry.
500 million. You could buy a fleet of private jets, or apparently one very smart file of weights and biases. So, Daniel sent us this prompt today about the pre-training bill. He wants us to break down the astronomical compute, the petabytes of data, and the sheer financial madness required to create a base model. And specifically, he wants us to distinguish this raw engine from the polite chatbots we actually interact with. By the way, speaking of frontier models, today's episode is actually powered by Google Gemini 3 Flash.
It's poetic, isn't it? Using the output of a massive pre-training run to discuss the cost of pre-training. But to understand why it costs $500 million, we have to start with what pre-training actually is. At its core, it's just one task, next token prediction. You feed a model a massive, unstructured corpus of text, the entire internet basically, and tell it, predict the next word, over and over trillions of times.
It sounds so simple when you put it like that. It's like a toddler learning to speak by eavesdropping on every conversation on Earth simultaneously. But there's a massive difference between that base model and the assistant that helps me write emails, right?
A massive difference. This is the core dichotomy our listeners need to grasp, pre-training versus post-training. Pre-training creates the base model. This is a raw autocomplete style engine. It understands the structure of language, it knows facts about the world, it can code, and it can reason to some extent, but it has no manners. It doesn't know it's an assistant. If you ask a base model, what is the capital of France, it might not answer you. It might respond with, what is the capital of Germany? Because it thinks it's completing a list of geography quiz questions it saw during training.
Right, because in its mind, if the previous text was a question, the most likely next text is another question, not necessarily an answer. It's just trying to match the statistical patterns of the data it was fed. It's essentially a mirror of the internet's collective output.
That's it. Post-training is what happens next. That's where you use techniques like supervised fine-tuning, or SFT, and reinforcement learning from human feedback, known as RLHF. That's the finishing school, where you teach the model to be helpful, harmless, and honest. But the bill we're looking at today? That's almost entirely in the pre-training phase. 99% of the compute budget is spent before the model even knows how to say, hello, I am an AI assistant.
Okay, let's look at the first line item on this bill, the compute. When people say thousands of GPUs, what does that actually look like in practice? Because I'm picturing a very loud, very hot room that could probably be seen from space.
You're not far off. For a state-of-the-art model in 2026, we're talking about clusters of 24,000 to 100,000 NVIDIA H100s or B200s. These aren't just plugged into a wall, they are interconnected with specialized high-speed networking like InfiniBand because the GPUs have to talk to each other constantly. If one GPU misses a beat, the whole training run can stall.
And these runs aren't just a weekend project. How long are we talking?
Usually 3 to 6 months of continuous 100% utilization. Imagine running a marathon at a full sprint for half a year without stopping. The reliability engineering involved is mind-blowing. Meta's technical reports on Llama 3 mentioned that at this scale, hardware failures happen every few hours. A cable snaps, a memory chip fries, a power supply blips. They had to build automated systems just to checkpoint the model, saving its progress, so they could restart from where they left off after a crash.
It's like playing a video game where you can only save every 4 hours, but the console explodes once a day. The stress on those engineers must be incredible. You're sitting there watching a $50 million electricity bill tick up, praying the cluster doesn't melt.
And the energy consumption is the silent killer on the bill. A single Frontier training run can consume as much electricity as 3,000 homes use in an entire year. We are seeing companies like xAI and Oracle building gigascale data centers now where the primary bottleneck isn't the software or even the chips, it's whether the local power grid can actually deliver enough juice to the building without causing a blackout.
Which explains why all these AI companies are suddenly getting into nuclear power and buying up land next to hydroelectric dams. They aren't just tech companies anymore, they're industrial power consumers. But okay, you've got the chips, you've got the power, now you need the fuel. Let's talk about the data bill. We're not just talking about a few Wikipedia articles here.
No, the scale has shifted dramatically. A few years ago, GPT-3 was trained on about 300 billion tokens. Today, Llama 3.1 and other frontier models are being trained on 15 trillion tokens or more. To give you a sense of scale, a token is roughly 3/4 of a word. 15 trillion tokens is essentially everything ever written by humans that has been digitized and put on the public web.
Is it just a giant vacuum cleaner? Like, if it's on the internet, it's in the model.
That was the early approach. Just grab everything from Common Crawl, which is this massive raw scrape of the web. But raw internet is mostly garbage. It's spam, it's gibberish, it's toxic comments, it's duplicate SEO bait. The real data bill isn't just the storage, it's the cleaning. This is a massive engineering effort. You have to run deduplication to make sure the model doesn't see the same Reddit thread 10,000 times. You have to filter for quality.
I remember reading about FindWebEdu from Hugging Face. That was a big deal, right?
Huge. They used AI classifiers to look at the raw web and say, is this page educational? Does it have high signal to noise ratio? By throwing away 90% of the junk and keeping only the high quality stuff, they found they could train models that were much smarter with less data. But developing those filters is itself a massive compute task. You're essentially using a small AI to decide what the big AI gets to eat.
It's like a digital kitchen. You have to wash the vegetables, peel them, and throw away the rot before you can even start cooking the soup. And if you mess up that data mix, if you put in too much Python code and not enough French poetry, the model's personality is baked in forever. You can't easily unlearn a bad data diet during post-training.
And that brings us to the actual dollar amount. In 2023, people estimated GPT-4 cost maybe $100 million to pre-train. Today, the stakes have quintupled. If you factor in the cost of the GPU cluster, which can cost billions to build, the electricity, the specialized datasets, and the salaries of the PhDs who know how to keep 100,000 GPUs from catching fire, you are looking at a total R&D bill that exceeds $1 billion for a single model family.
That is the definition of a moat. I mean, I have some decent savings, Herman, but I'm a few $100 million short of starting Corn AI. This effectively means that only, 5 or 6 organizations on the planet can play this game.
It's a very short list. Microsoft and OpenAI, Google, Meta, Anthropic, and maybe xAI. Then you have the Chinese state-backed firms. That's it. If you're a startup today, you are almost certainly not pre-training a frontier-level model from scratch. You are either fine-tuning someone else's model, or you're building on top of an open-weight base model like Llama. The compute divide is real. It's becoming a game of whoever has the most capital and the best relationship with the power company.
It's fascinating because it changes the whole garage startup myth of Silicon Valley. You can't build a frontier LLM in a garage because the garage doesn't have a dedicated substation and a $100 million credit line with NVIDIA. But let's look at what actually comes out the other side of this month's long, multi-million-dollar process. You have a base model. If I were to interact with a raw base model right now, how would it feel compared to the ChatGPT I'm used to?
It feels like a brilliant, chaotic ghost. If you give it a prompt like, the best way to cook a steak is, it will do an amazing job. It will give you a list of instructions that sound like a professional chef. But if you ask it, can you help me cook a steak? It might respond with, can you help me bake a cake? Can you help me roast a chicken? It thinks you're writing a children's book about helpful animals.
So it's a pure mimic. It doesn't have a sense of self or a mission to be an assistant. It's just completing the pattern.
Right. And here's the kicker. Some researchers argue that the base model is actually more capable than the chatbot version. When we do post-training, the RLHF and the safety tuning, we are essentially lobotomizing parts of the model. We're telling it, never say this, always respond in this specific tone, don't be creative in these ways. It makes the model safe for a corporate environment, but it often reduces its raw problem-solving edge or its out-of-the-box thinking.
That's wild. So we spend $500 million to build a superintelligence, and then we spend another few million to make it act like a polite, slightly boring intern.
It's a necessary trade-off for usability, but for developers, understanding that base model is crucial. If you're building a specialized tool, sometimes you want to start with the base model and do your own fine-tuning because you don't want the preachy behavior that comes with standard RLHF.
Okay, let's dive into that post-training stack for a second, just so we can really see the contrast. Daniel mentioned SFT, RLHF, and DPO. These are the tools that take our chaotic ghost and give it a name tag and a job description. How do they work, and why are they so much cheaper than the pre-training?
They're cheaper because they work on much smaller datasets. While pre-training uses trillions of tokens of dirty web data, SFT, supervised fine-tuning, uses maybe 10,000 to 100,000 gold. Examples. These are high-quality conversations written by humans. User asks X, assistant responds with Y. This teaches the model the formats of being a chatbot. It's like teaching a genius who has read every book in the world how to actually answer a phone call.
And then RLHF is the ranking phase.
Reinforcement learning from human feedback. You show the model two different answers to the same question and have a human say A is better than B. The model then updates its internal reward function to prefer the style of answer, A. It's how we train it to not be rude, to be concise, and to follow safety guidelines.
And you mentioned DPO, direct preference optimization. Is that the new hotness?
It is. It's a 2024 2A25 breakthrough that basically skips the complicated step of building a separate reward model. It just uses math to directly optimize the model based on those human preferences. It's faster, it's more stable, and it's why we're seeing such a rapid explosion of high-quality instruct models. A small team can take a base model and do DPO for $10,000 and a few days of compute. That's why you see so many variants of llama on Hugging Face. The polishing is cheap. The quarrying of the stone is what costs $500 million.
I love that metaphor. Pre-training is quarrying a massive block of marble from the mountain. Post-training is the sculptor coming in with a chisel to make it look like a person. You can't sculpt if you don't have the marble, and only a few companies own the mountain.
And the mountain is getting harder to mine. We should talk about the data wall. This is a big topic in 2026. We have basically used up the high-quality human text on the internet. We've scraped the books, the code, the papers. So now, companies are turning to synthetic data, using AI models to generate data to train the next generation of AI models.
That sounds like a recipe for digital inbreeding. If a model learns from its own mistakes, doesn't it just get weirder and weirder until it collapses?
That's the fear, model collapse. If the synthetic data isn't carefully curated, the model loses the nuance of human language. It starts repeating its own quirks. But, interestingly, if you use a stronger model to generate data for a smaller model, like using GPT-4 to train a small coding model, it actually works incredibly well. It's like a teacher writing a textbook for a student. The data bill is shifting from pay for scrapes to pay for high-quality synthetic generation.
It's an interesting pivot. So the moat isn't just about having the most data anymore. It's about having the best teacher models to create the next generation of data. It's a self-reinforcing cycle. If you have the best model now, you can use it to build the best training set for your next model, widening the gap between you and the competition.
And that's why the engineering talent is such a huge part of the cost. You need people who understand the alchemy of the data mix. There was a recent case study on a 1.8 trillion parameter model where the researchers found that adding just a tiny percentage of high-quality textbook data late in the pre-training run had a massive impact on the model's reasoning abilities. It's not just about quantity, it's about the timing and the blend.
It really does feel like digital alchemy. You're mixing these massive vats of data and compute, hoping the Philosopher's Stone comes out at the end. But what happens if the run fails? If you spend 3 months and $50 million in electricity and the model comes out stupid?
It happens. More often than these companies like to admit, sometimes a model develops a mode collapse where it just starts repeating the word "the" over and over. Sometimes the loss curve, the mathematical measure of how well it's learning, just flatlines for no obvious reason. That's why these labs run miniature versions of the training first. They'll train a tiny 7 billion parameter model on a slice of the data to predict how the 1 trillion parameter model will behave. It's called scaling laws.
So they're basically doing wind tunnel testing before they build the actual jet.
Precisely. If your scaling law prediction is off, you might waste $100 million. This is why guys like Sam Altman and Dario Amodei are so obsessed with compute. They're betting that the scaling laws will keep holding, that if they just keep paying a bigger bill, the models will keep getting smarter.
But at some point you hit a physical limit, right? Not just the money, but the literal atoms. We're already talking about data centers that need their own dedicated power plants.
We are. We're seeing a shift toward more efficient architectures. You mentioned state space models and Mamba in your notes, Corn. There's a lot of research into sparse models like mixture of experts where only a fraction of the model fires for any given prompt. That's how GPT-4 and Llama 3.1 405B managed to be so large but still relatively fast. They aren't using all their brain at once.
It's like a giant library where only the librarians relevant to your specific question get up from their desks. It saves a ton of energy, but the bill to build the library in the first place is still there. You still have to pre-train all those experts.
Right. The bill for the initial training doesn't go away. In fact, for mixture of experts, the pre-training can be even trickier because you have to balance the experts so that one doesn't become too smart while the others stay lazy. It's a massive load balancing problem.
So, looking at this from a business or developer perspective, what are the actual takeaways? If I'm a CTO sitting on a pile of cash, do I try to build my own mountain? Or do I just rent a room on someone else's?
For 99.9% of businesses, you rent. The takeaway is, don't confuse a base model with a product. If you're using an API, you need to know if you're hitting the base endpoint or the instruct endpoint. If you want a chatbot, use instruct. If you want to build a very specialized tool, say something that translates legal jargon into plain English, you might actually get better results by taking a base model and doing your own SFT on a few thousand high-quality legal documents.
And for the average person listening, the takeaway is probably just a bit of healthy respect for the sheer industrial scale of what's happening behind that little blinking cursor. When you ask it to write a poem about your cat, you are utilizing an asset that cost more than a skyscraper.
It's the centralization of intelligence. We used to think the internet was this decentralized, democratic thing. But the engines of the internet, the frontier LLMs, are becoming some of the most centralized assets in history. Only a few entities can afford the bill. That has huge implications for who gets to set the safety rules, who gets to define truth for these models, and who gets access to the most powerful tools.
It's a high-stakes game, and I wonder if the bill will ever actually go down. We've seen this in other technologies. The first computers cost millions and filled rooms. Now we have them in our pockets. Will we ever see frontier pre-training become affordable for a mid-sized company?
It's a tug of war. On one side, we have better algorithms and more efficient chips. On the other side, the frontier keeps moving. As soon as it becomes cheap to train a GPT-4 level model, the big labs move on to GPT-5 or 6, which cost 10 times more. We might be in a permanent state where the latest and greatest is always priced at the limit of what a multi-billion-dollar corporation can afford.
So the moat isn't a fixed wall, it's a moving target. You have to keep running just to stay in the same place relative to the frontier.
That's the reality of the AI arms race in 2026, and it's why open source or open weight models are so important. When Meta spends $500 million to train Llama and then releases the weights, they are essentially giving a $500 million gift to the developer community. They're subsidizing the data bill and the compute bill for everyone else.
Although, let's be honest, they're doing it because it hurts their competitors and builds an ecosystem around their hardware standards. It's generous with a side of calculated strategy.
Oh, absolutely. There are no charities in the frontier AI space. But regardless of the motivation, the result is that we get to play with these base models without having to pay the bill ourselves.
Well, I for one am glad I'm not the one trying to explain a $50 million electricity bill to a board of directors. I'll stick to the cheeky observations and let the PhDs worry about the GPU failure rates.
And I'll stay here reading the technical reports on how they fix those failure rates. It's a win-win.
Before we wrap this up, there are a few practical things for people to keep in mind. If you're a dev, go play with the base models. OpenAI and others often have base versions available through their APIs. Try a prompt on a base model versus the chat version. It's a great way to see the raw intelligence before the filters are applied. You'll see why people call them stochastic parrots, but you'll also see the moments of genuine, weird brilliance that often get polished away in the assistant versions.
And for the business leaders, invest in your data. The bill for pre-training is high because data is the fuel. Even if you're just fine-tuning a model, the quality of your internal data will be the differentiator. A mediocre model with perfect data will often outperform a frontier model with messy, irrelevant data for a specific task.
Good point. The data kitchen is still the most important room in the house. We actually talked about that back in episode 1839, AI's data kitchen, if you want to hear more about the hoovering side of things.
I think we've itemized the bill pretty thoroughly. Compute, data, power, and the ghost in the machine, base model that comes out the other end. It's a wild era to be watching this stuff.
It really is. And that's our look at the staggering cost of birth for an LLM. Thanks as always to our producer Hilbert Flumingtop for keeping the lights on, at a much lower cost than a GPU cluster, fortunately.
And a big thanks to Modal for providing the GPU credits that power this show. They make the compute bill a lot easier for us to handle.
This has been My Weird Prompts. If you're enjoying these deep dives into the guts of AI, we'd love it if you left us a review on Apple Podcasts or Spotify. It's the best way to help other curious humans, and maybe a few curious bots, find the show.
Find us at myweirdprompts.com for the full archive and all the ways to subscribe.
Catch you in the next one.
See ya.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts.